talk about what enthalpy is again, why we care, and what are the different ways that we can find enthalpy. The sum of all of the energy of a system is called its internal energy. That sounds like a really useful quantity. Enthalpy, on the other hand, is the sum of all the energy in a system, excluding work. So why do we talk so much more about enthalpy if it is a less comprehensive term than internal energy? The reason that we talk so much about enthalpy is because enthalpy is extremely effective in a constant pressure system. And when I say constant pressure, you should hear an open system. Because so much of our world happens in an open system, meaning matter and energy can transfer freely in and out of the system and the surroundings, enthalpy is an extremely useful quantity because we can apply it to so much of everyday life. That being said, there are three main ways that we talk about finding enthalpy. The first way that we talk about finding enthalpy is through what we call constant pressure calorimetry or coffee cup calorimetry. This type of calorimetry can literally be done with a styrofoam cup from a gas station. This is an experimental way to find the enthalpy of a reaction. You would put it into your cup and you would measure the temperature beforehand, the temperature after, and the mass of everything in your cup. Then you can use the first law of thermodynamics to determine what the enthalpy of that reaction was. This is an excellent method, but it's not always possible because there are some reactions that happen very slowly. Now, if it's an open system, that means your gases are going to be exchanged between your system and your surroundings, but also the heat can escape. If you're measuring the change in temperature, you need the reaction to happen quickly enough that you can measure that change in temperature before all of the heat is transferred to the surroundings. So if you have a reaction that happens very slowly, for example, the oxidation of zinc is a pretty slow reaction. That reaction would take so long, it would be impossible to tell the change in the temperature because the surroundings would fluctuate so much and the heat would escape. It wouldn't be possible to measure it. So in that case, a method that you could use would be Hess's law. Hess's law relies on the fact that enthalpy is a state function. So if you can have any number of reactions that you can actually use calorimetry to measure, and in the end you can rearrange them and add them up so that they equal the reaction that you're looking for, then that reaction's enthalpy is dependent only on what you started with and what you finished with. So it doesn't matter how you got there. So you can use Hess's law as a theoretical way to calculate the enthalpy of a reaction that is too slow to measure directly in calorimetry. Another way that you can calculate the enthalpy theoretically rather than experimentally is using standard enthalpies of formation. This is another theoretical way to calculate it, but it's based on experimental evidence. An example of a reaction that you might use a standard enthalpy of formation would be the rusting of iron. Again, it's a really slow process, so it's not a good candidate for calorimetry. But it may be difficult to find reactions that you can measure in calorimetry that add up to the reaction of the oxidation of iron into rust. In that case, the standard enthalpy of formation would be a great theoretical way to predict what the enthalpy of that reaction would be. If you have a reaction where you can use all three of these methods to find the enthalpy, then there will be really good agreement between all three. So all of these are really good ways to find enthalpy, but why do we care about how much heat is transferred in and out of a system? This is an extremely useful way for us to relate energy and matter. For example, different materials have different energy density in them. Why might we burn natural gas instead of coal? Well, natural gas is cleaner, but also it has a higher energy density than coal. So we get more energy per mole of the substance than we would with coal. And the reason that we know that is thanks to enthalpy.